Good evening. So I think everything on this slide Tom has covered already about the, of course, I think, so I go to start off with just the view from geostationary orbit, which is something many of us have grown accustomed to seeing because of all the GOES weather satellites showing the cloud images. And this is such an image. And Superstorm Sandy is here off the coast of the U.S. And these sorts of images, it's certainly very appealing to sit there and see the whole Earth all at once rather than just a little piece of it at a time and have to piece it together. And this sort of view, of course, for the type of the space environment for the Thermosphere Ionosphere system, which is an important part of the space environment, has some advantages, being able to have this view to provide context. It's a view that we've never had routinely. Only occasionally have we had data of this sort of view. So some of us began dreaming of doing this, but at least I began dreaming of it back in 2004 when it became news about an AO coming out shortly for proposals for a UV imager. Well, it wasn't just for UV imager, it was part of RBSP mission. And one of the things that they suggested as a possibility for missions of opportunity, which is in addition to the main satellite, was UV imager. And there were actually 4 teams that proposed UV imagers, and that's the way we got started. Now it's 2004. You say, why did it take us so long to build it? I'll get to that later. That's sort of perseverance, I guess. So of course, this isn't. Other people have been thinking about this sort of view and have even further back. George Carruthers at Naval Research Laboratory, back on Apollo 16, he flew a far ultraviolet camera that used film and took pictures of the Earth from the moon. And these images show sort of some important aspects that you can have or that you can get simultaneously from this perspective from a long distance from the Earth. It's got, you can see here that there's these bright emissions or bright areas are actually emissions from atomic oxygen, or primarily atomic oxygen. It was a sort of a broad wavelength range, but most of this emissions from atomic oxygen. And on the day side, of course, we call this a daytime air glow or day glow, and that's produced by the sun's EUV energy being deposited into the Earth's atmosphere and causing emissions from the upper atmosphere. Also, down here at the bottom, you can see the Aurora, which occasionally you see here in Boulder when there's a lot of geomagnetic activity. The northern lights, the Aurora come down, and you can see this spectacular displays. Of course, this is something that from geostationary orbit, depends on where you are, you would routinely see the Aurora at least one northern or southern latitudes, depends on your location. And you can also see the equatorial, at night there's some equatorial ionization anomalies that occur in the nighttime. And these regions in particular, have some important effects on radio frequency propagations which affects things like communications, navigation, and a lot of just ranging of radar for determination where satellites are, things like that. Okay. Now, although we don't have any geostationary images like that, have never had really those sorts of images routinely, we have some great models of the Thermosphere Ionosphere system. This is a region, a lot of these emissions that we're showing here it's from a model that's calculation that Stan Solomon at HAO did, and most of these emissions come from approximately 160 kilometers in the Earth's atmosphere. This is relatively low in the atmosphere. It's a region where satellites can't stay up very long, and consequently we don't know a lot about this region just because of the difficulty in measuring it. Remote sensing, of course, is a good way of doing it, but there's remote sensing techniques are, you got to figure out a technique that works to provide you the information that you want, and Mother Nature only provides you so many things to use, and we're learning better how to use them. And this is one of the things that we did on gold, is to figure out that we could use some of the emissions to learn more about the Earth's atmosphere. Of course, again, they've got the day glow on the day on this side. This is 1356 nanometer emission, which is primarily atomic oxygen. And at night, you have, of course, the equatorial anomaly. At the same time, the gold imaging, although this only shows the 1356, you also get images of the N2 emission on the day side, which is molecular nitrogen, the same gas that's down here on Earth that makes up most of our atmosphere is also up there. And these, the emissions that come from this region of the atmosphere, we can use to learn, provide us key information about the atmosphere, what's happening in this region of the atmosphere, the temperature, the composition, see how it evolves over time. This how it evolves over time is really the focus of the mission. We have 4 science questions that we've laid out to look at that the mission will address. Really, we're looking, I guess in simple terms, we're looking at the forcing from above and from below in the atmosphere. The geomagnetic storms and the solar short wavelength radiation is something that we've been looking at for decades. There's a lot of variability. There's sources of energy coming into the atmosphere. Consequently, it causes variability in the Earth's atmosphere, in the ionosphere. In recent years, it's become clear that there's a lot of forcing also from below, that this is a significant piece of the variability, significant source of variability in the atmosphere, that is tides and waves and stuff propagating from the lower atmosphere up further into the atmosphere. When they get up into the atmosphere, both these sources affect the nighttime ionosphere, which is one of the things we'll be looking at. That equatorial anomalies that was pointed out earlier. We're looking at how some of these influences from the day side will affect the night side, the tides and waves, some of those influences. So from geostationary orbit, you're sitting in one location, so you can sit there and follow throughout the day how things are evolving. Then you watch the same region at night, at least most of the night. I'll get into that a little bit later. There is a region at time in the middle of the night when we'd be looking back at the sun. And these emissions we're looking at are relatively weak. So an instrument that's designed to look at these emissions, if you look at the sun is one of the brighter sources in the sky, if I remember correctly. so it's really a traumatic experience for a UV instrument to do that. It's not recommended in the owner's manual at all. I've worked on one instrument that did that, and it was, it worked afterwards, but it wasn't really as happy as it was beforehand. So I know from experience that that's not the thing to do. Talked about, of course, the solar geomagnetic forcing from above. And this diagram just gives you an idea of the magnitudes of these and the importance of these. Most of the time, the solar EUV and X-rays are the dominant source of energy into the upper atmosphere. But there are times when, during geomagnetic storms, when the Joule heating is the dominant source of energy, significantly exceeding what's happening in what the sun's doing. And of course, this shows it through 3 solar cycles. As you probably know, there is approximately 11-year dependence in the sun's output, and so the solar EUV varies in that time scale. There's also short-term variations due to flares and just variations in the sun's output itself. Now, these, of course, are depositing energy in the upper atmosphere, what I've referred to as the Thermosphere Ionosphere. And just looking at the thermosphere is the neutral part of the atmosphere. So this is the tutorial part here for just a moment, just so it can just give everybody context. So at solar minimum, the atmosphere is approximately, if you look at a model, the atmosphere reaches a temperature of approximately 700 degrees maximum. At solar maximum, it depends on the solar maximum. Of course, the last one is pretty disappointing. It reaches, over 1,000 degrees. Now, due to the geomagnetic storms, you can actually have this amount, approximately this amount of variation within a short time, within a day, or just because of geomagnetic storms. But this is just assuming the sun's constant, which it isn't, but this is approximately the levels you'd expect. And again, here's just pointing out, here's approximately the altitude of the disk data that GOLD will be observing. So, of course, this is the neutral atmosphere. At the same time, that was just showing the temperature. At the same time, the densities are also varying. Unlike here on Earth, where it's all molecular oxygen, almost everything is molecular oxygen and molecular nitrogen until you get up to, it's pretty evenly mixed up to about 100 kilometers. And once you get up to about 100 kilometers, then all that UV radiation, the short-wave stuff, starts tearing the atmosphere apart, literally. So it's just takes the molecules, tears them apart. And you actually wind up with a lot of atomic oxygen. And there's some atomic nitrogen also in the higher altitudes in this region we're looking at. And these components vary, the composition varies, depends on the conditions, and this variation can cause a lot of variations in the ionosphere also, as well as just the production of it affects the how long it lives. So anyway, this region of the atmosphere can change very dramatically. We walk out, and if we get tens of degrees swings in a day around here. Florida is even less. It's like only about 10 degrees from night to day. So really disappointing. In the summer, for me in Florida, where I live in Florida, that it's a really hot day, and I'm from used to the idea everywhere else I've lived that you go out at night and it's going to be cool because it cools off 20, 30 degrees at night. It's only about 10 degrees in Florida. Anyway, at these altitudes, it's in comparison to what we're used to seeing here on Earth. At these on the Earth's surface, it's really dramatic. We can have hundreds of degrees, several hundred degrees variation in just a short time. 300 or 400 degrees is not atypical for the variations. As I mentioned earlier, some of the changes in the space environment, thermosphere, ionosphere, sometimes we refer to this at least as a portion of space weather, that these can affect a lot of the systems we depend on, the communications, navigation, satellite TV. You'd think that due to the geostationary satellites, most regions of the Earth, signals from geostationary satellites go through those equatorial anomalies I was showing you earlier. Most regions of the Earth actually are affected by those at night. I showed them they're sort of at low latitudes, but it depends on during storms. They can actually move to higher latitudes, and most places, the places most of us live, are at least at times can be affected by those. So it does have effects on a lot of systems that we depend on. Now, I talked about the higher altitudes. Then we're talking about the stuff, the forcing from below. There's a lot of, these are just some examples of show some ideas of the tides, actually this is the winds in meters per second. In conjunction with the winds, you actually have temperature changes also. Remember that so you go up in altitude, you move the gas up in altitude with winds, and pressure's less, so it actually would cool. So there's a lot of different tides. A lot of work's been done with the SABRE data from timed. Most of the stuff is at 100 kilometers or below. Expectation is that the stuff will reach higher altitudes, but it's not clear how much or what reaches higher altitudes. Sometimes there are some measurements, limited measurements at really high altitudes that show some tidal effects, but most of the stuff, a lot of these tides are filtered in the region around 160 kilometers and lower, and we really don't have a good picture of that, and that's one of the things GOLD will be looking at. Of course, those are tides and waves. A lot of that's generated. Actually, some of those are generated internally, but this is stuff that's generated lower altitudes. What this is some calculations by Hanley Liu at NCAR HAO, and this is from a typhoon in the Pacific. And you can see these are actually the temperature perturbations that you get at 110 kilometers. This is not the typical calculation that they do, because it's really high resolution and allows you in altitude and in spatially, and it shows tremendous activity in gravity waves. Again, the expectation is that some of this stuff, we don't know how much, depends on the winds that are slightly around 110 to 150 kilometers, depending on those winds as to what gets through to higher altitudes. But even at these altitudes, there's significant perturbations in the temperature. So these would have, as you go higher, remember the waves breaking on the beach, how as it gets shallower, the wave gets bigger. The same thing happens in the atmosphere. As you go higher in the atmosphere, there's less density. So the perturbations that you get will be even larger as you go to higher altitudes, if they reach that altitude, if they don't break and dissipate the energy at lower altitudes. And even if they dissipate the energy at slightly lower altitudes, you still may can see some effects at higher altitudes. And this is, could be a significant, or at times can be a significant source of energy into the Earth's atmosphere in the lower thermosphere. So I talked earlier about how we started this back in 2004. So let me just history here. So this is a chance to reminisce. That was RBSP. We were GOLD selected for a competitive phase A, and of course the reason it's taken us so long is they didn't, they liked it but not enough to fund it. But we were funded for extended phase A. So that was the good news. We got debriefed in December 2007. That's when the debriefing was. And our next proposal was in January 2008. Actually, it's January 15th. And this is December, December the 5th. Remember, it was AGU. We had the debriefing for this. And January 15th, the proposals were due. So that was a very busy holiday, not with celebrations or eggnog or anything like that. So anyway, we were actually, this time we were what they called a partial selection. They had an Astro mission was selected that had as a MOO, that had a flight opportunity on a Japanese satellite, and a mission of opportunity. On a Japanese satellite that was, sort of a one-time deal. And as I'll talk about in a minute here, we were teaming up with the commercial guys, and the idea is they've got multiple satellites, so okay, well you guys can catch a later ride, right? Maybe we'll come up, maybe you can get the price down, the cost down, and maybe we'll come up with the money. And they didn't, so okay, we get to try a third time. This time it took. This is we started selected for funding in 2013. So I guess the moral of the story is, if at first you don't succeed, try again and again. And so it took us 3 times, so we made it. So today we're the third round of this have been successful, and the result is the GOLD mission. Now, of course, the SES. The satellite we're flying on is a geostationary bird. These things are, this one is I'll talk more about it in a minute, but it's going to be located, it's supposed to be scheduled for launch, well, let me back up. It's going to be located basically over the mouth of the Amazon, is where this is, 47.5 degrees west. So they're providing communications to Brazil, and they've, the schedule is of launch late 2017. You know, that hasn't firmed up yet. So maybe a little bit later in late 2017, you know, like early 2018. But we don't know at the moment. But usually these guys, they're commercial guys. They have a quarter in mind, and if someone starts pushing them out of getting launched in the quarter they planned on, from what the explanations I've gotten is someone's probably paying them money if they're not delivering in time to get them up in the quarter they expected. One interesting thing about this is it's electric propulsion all the way once it gets off the ground, which was a surprise to us until I think PDR, and someone asked the question, and then the SES guys were saying, "Oh, we were afraid you're going to ask that." So that's okay. It's an interesting experience. The instrument is a two-channel. Basically, it's two identical channels. It's an imaging spectrograph, two identical channels, and each of them observes in this wavelength range, the far ultraviolet wavelength range, and that's lets us do the remote sensing we want to do. Gives us data we need to produce the products. Some of them listed here. We're using, of course, UCF has the Science Data Center, so that's where I'm located, in UCF. Just to give you a little context on SES, this is somewhat dated. I don't have them. This is from 2015, and they had, like, at the time, 55 satellites in orbit. These things have lifetimes typically of about 15 years, and even with that many satellites, you can do the arithmetic pretty quickly. 15 years, lifetime, 55 satellites. You need to put up about 3 a year just to keep your fleet in keep maintaining your fleet. So they have these guys are, I think them and Intelsat are the two of the biggest commercial companies providing communications. I don't know which ones, sort of, at least a year or two ago when I was keeping closer track of this, it sort of, went back and forth as to who had the most satellites up. The satellite we're flying on it is built by Airbus Defense and Space. It's this E right here means it's electric propulsion. Because the launch vehicle, now having watched it's a Falcon 9. Remember that spectacular? Did anybody miss that spectacular Falcon 9 episode a few months, basically last fall, I think it was, where they're having on the ground, they had some sort of testing they were doing with one of the launch vehicles, and they had the satellite on it, and the whole thing just was a great display of fire and raining satellite parts. so when a week ago when the satellite went off, they are launching now. They actually reused a satellite last week, and it was SES also, another Falcon 9, reusable. I guess what they call it. I think they use the terminology flight proven. Is what they that sounds better than second hand, right? But I was relieved to see it went off smoothly. It was an SES launch. It was SES-10, I think, they put up with that satellite or that launch vehicle. I think I mentioned about the launch vehicle. We're still that's what we're slated to go on. I talked about the electric propulsion already, and the dry mass is approximately 4.5 metric tons. So these things are pretty substantial satellites. I guess it's light. It's the electric propulsion. You have big tanks of xenon. That makes that sucker really light. Only 4.5 tons. That's what they tell me. I asked them, one of the guys, well, if it's a chemical propulsion, how heavy would it be? oh, 7, 8 tons or something like that. And I'm thinking, oh boy, this is, anyway, it's a different world than it's the opposite end of the spectrum from CubeSats, which some of you are familiar with. Just to give you an idea of how big this thing is. Now, I thought it was interesting to have this in millimeters, so I had to do the calculation. If you do it really fast, you'll know that it's about 49 yards tip to tip, this thing is. So it's about half a football field. These things are really a big satellite. Now, other thing I will touch on here is you've seen the little where's you've seen the Where's Waldo books with kids? Okay, now this is the Where's Gold picture, right? So now you're at a disadvantage because you don't know what you're looking for, because everything's gold here, you say, right? The whole thing is gold. All right, so I'll give you a little help here on where the gold is. And this is actually the only picture I have of the thing. I have pictures of the instrument, sort of artist rendition of the satellite. This is the only one I have of the two together. Since the instrument is not on the satellite yet, I'm still, someday maybe I'll have a picture actual picture, but these are artist renditions, so it gives you an idea of the scale of the satellite in comparison to the instrument. This thing is about 2.5 meters by 3 meters. The top deck is, and I think the thing is like 7 meters height. So it's a big satellite. The instrument itself, built here at LASP, has the 2 channels. I'll give you some sort of vital statistics here. And we had at some point we had predictions of mass, and sort of surprising, we came in right on the nose of where we expected to be. This is actually we could have been a little bit lighter here. We added some extra shielding because we had some mass margin that we had bought from these guys, sort of agreed to pay for. And since we had to pay for it up front, we said, okay, a little bit more mass for shielding would improve, cut out a little bit of radiation noise in the detector. We've got the mass, we got the shields, so let's just put them in. So it would have been about 35 if it hadn't been for that. The other thing the nice thing about being on a communication satellite is it's designed to give you lots of signal down. So you want 6 megabits per second continuously, it's no problem, right? You want 12, they could do that. This is one of the fabulous things. It's data rates that most science missions can only dream about. But we've got a whole satellite. What they've done is they have a transponder on there that they're feeding our signal to. That dumps it to the ground. It goes to a ground station in Virginia. Actually, is where it'll be. The ground station will be receiving it, and it'll come to LASP. So, it doesn't. I guess if we the data rates, like I said, data rate isn't a problem. Powers, is not a problem. This thing generates tens of kilowatts. It's early in life. Powers, okay. You want another 10 watts? Okay, no problem. You start getting over 100 watts, they start, that's sort of the threshold where they start thinking about asking a few questions. But 60 watts, 70 watts, okay, that's not a problem. Sort of strange to think you can just, okay, 10 more watts, okay, so what? And just some beauty shots of the instrument itself, actual instrument, and while I was here at LASP, and actually a picture here with some of the engineers moving the instrument, just to give you an idea of the scale of the instrument. So it's that's not that big. It's about the size of a microwave oven, just crudely. It's a lot heavier than a microwave and a lot more power hungry than a microwave, but it's approximately the size of it. And now it's over in France at Toulouse, sipping French. You know, these bottles of French nitrogen back here. It's sipping French nitrogen, enjoying it. It loves the stuff. So anyway, we were doing some post. This was actually at the delivery of the instrument. We were doing some checkout of the instrument after it's delivered. So we were doing some pump out on it. That's one of the few pictures I have of it in Toulouse so far. Just to give you an idea of how the instrument works, as I mentioned, it's an imaging spectrograph. So in imaging spectrograph, you have to have a slit for most. This has a slit, so and the slit is only long enough to go about half the latitudes we want to cover if we're going to look at the whole disk. So it just uses a two-sided mirror. So it depends on which side of the mirror you're using as to whether you're looking at the northern latitudes or the southern latitudes. And we can scan it east-west to scan across the Earth. Of course, we're looking at the dayside. We'll occasionally do stellar occultations, look at a star. On dayside or night side, we can do that. And you know, we also do some limb scans of the N2 emission. That gives us some information about the exospheric temperature, TXO. And on the night side, of course, we do those low latitude equatorial anomalies we look at. And just to give you, show you, this is a calculation. We actually have some spectra from the lab, which I could have used, which show something very similar to this. They don't have the atomic oxygen and atomic nitrogen emissions in them. Most of the emissions here are just the molecular nitrogen that we have here on Earth. Those emissions, because they're molecular bands. We also have looking at a couple of atomic emissions. By ratioing these atomic oxygen to molecular nitrogen, we can get information about the composition of the upper atmosphere. By looking at the shape of these bands, we can get information about the temperatures. And some of the other information we can get out is detailed here. For example, we can look at from stellar occultations. It's a way we can get the O2 density profiles. O2 doesn't emit in this wavelength region, but it absorbs. So that's the way we can get at that, the sort of three major components of the atmosphere, the oxygen, the atomic nitrogen, and atomic oxygen. Excuse me, molecular oxygen. Any questions? Yeah, everybody. Yes.
Your diagram indicates a vertical slit that you move across the disk to produce an image. Is that a line of pixels then somehow?
Correct.
Does each pixel take its own spectra?
Yes, it does.
Okay.
So, I should have commented on that earlier. Pixels, we say pixels, but in reality, it's a 2D imager, and that's the great thing about the bandwidth we have. We don't feed down pixels. We actually feed down the locations of every pulse.
So you're moving a spot or a virtual spot, scanning the surface.
Well, it's a whole slit. Okay. It's a whole slit. So along that slit, we have spatial information. And I'll show you a little bit more a simulation later that shows also not only the slit scanning but the spectrum. So I think that'll help make it a little bit clearer. I think the view I have, I'm not sure whether that's the next slide or not, but because what I'm trying to point I was wanting to make was that each location, wherever the photon occurs on the detector, is a 2D detector. We get the location, XY location, and the pulse height. We feed all that down. So on an orbit, we don't have to be very smart.
Does the pulse height give you wavelength?
No, it's the locations. One of them gives us the wavelength. The other one gives us position. Other is position along the slit. So we get the two dimensions, One's along the slit, which is spatial location, north-south, and the other one, for this one slit position, we'll have a whole spectrum in the other dimension. And the pulse height allows us on the ground to decide what, if there's spurious pulses, we don't have to filter them on orbit, we just feed them all down. So we can, after the fact, if we decided that we didn't do this correctly, we can go back and do the filtering differently for the pulse heights. Yes?
How's the scan made?
The scan,
Spatial scan.
it's just a two-sided mirror and just rotate it around. So it depends on which side of the mirror you're using as to whether you're looking at the northern latitudes or southern latitudes. So it's a very simple scan mechanism. So we basically don't have any other north-south. There's really no north-south motion. There's only motion in one direction with the scan mechanism. So it just rotates the mirror around. It's a two-sided mirror.
Yeah, that's the north-south. What's east-west?
East-west, we do rotate the mirror.
Yeah.
So you just rotate it. We can control it. We can stop it anywhere we want to. We can control the scan. We can control the rate at which it moves. So we can actually have it dwell in one location, only look at a portion of the Earth if we want to, or the whole Earth, or even off the Earth if we wanted to do that. And there's 3 slits in it also. I didn't meant to talk about that, but it does have, for the occultations, we have a really wide slit that we can put out there, and it encompasses the whole limb region, so we can do the whole occultation without moving the slit. Is what we do. So it's a wide slit to do that. There's another question. I'm sorry, there's enough noise here.
Mine's kind of a layman's question. I guess, I heard the Air Force had registered oxygen going up to you have O2, then of course O3, the ozone, but I heard it's been registered up to O21. That's not something you guys have ever really got involved.
No, we're not. The oxygen we're looking at, we're looking higher in the atmosphere. The ozone's all gone for the altitudes we're looking at. It's just atomic oxygen and O and O2 is what we're seeing.
This is another kind of, I know it's kind of been specifically germane to what you're lecturing on, but I heard the Germans just not too recently put up a couple of satellites and they're actually measuring the deviation in the Earth's magnetic field. I don't know if you had heard very much about that. It ties into the magnetic poles changing, or north and south.
Well, I guess, of course, we see the Aurora. We will see the Aurora in the northern latitudes, but we don't, that's really the only effects of the magnetic field we have. I think, is that what you're asking?
I heard there was actually an airliner that had to deviate from its flight plan because of the, I don't know if it was a solar flare or if it was...
Oh, yeah, yes. That can happen. That can happen because if there's a lot of earlier I was showing you that Joule heating during the geomagnetic storms. There's also a lot of particle energy, and they do divert the polar routes if there's a lot of really high geomagnetic activity because the radiation dose is significant. So, and NOAA, that's one of the things NOAA does is provide that information about the forecast for those sorts of routes. Yeah.
Back to the topic of stellar occultations, are you going to be using lunar occultations?
Am I going to be using what now?
Are you going to be watching things like the moon through the atmosphere, and also following things like other spacecraft as they just go around the edge of the limb? Your occultation opportunities.
We will see the moon, but the other spacecraft, I think, we're so far out.
Not only look at the moon. I mean, so you're sitting here, you're looking at Earth. Sometime the moon's going to be back there.
Yeah.
And as it moves through, that gives you an excellent opportunity. It gives you a bright, calibrated source that you can go against in the atmosphere.
Yeah. So yeah, we will be using. Actually, we'll probably be relying on stars for the stellar for the calibration. We hadn't really thought a lot about the moon itself.
The moon's bright.
Yeah.
Okay, or it can be dim. I mean, you can get an Earth side. It's calibrated by virtue of the fact that you're basically getting reflected sunlight.
Yeah.
So there's some absorption band differences in there, but I mean, it's easy to get at in that way.
Yeah.
But in that way, I know you said you use a larger slit for for the occultations.
For the occultations, but we have narrower slits, which if we want to look, you know, if when we're scanning, we will be seeing the Earth. We will at times see the moon.
So is the width of that slit a function of the flux from the star?
The width of the slit, if we're doing a stellar occultation, we have a point source, so we don't really, that is really determines, essentially becomes is like you don't need a slit, a narrow entry slit for that case. But the whole, as the star goes through the wide slit, the whole spectrum will actually shift slightly as the position in the slit shifts. Because essentially, think of it as your entry slit is moving position just slightly. Is what we're doing.
Well, most of the time we use wider slits on dimmer targets just to get more flux.
Well, we do have some two slits for that reason. One of them's narrower than the other. We had one of them slightly wider to use at night if we need more signal. But for the stellar occultations, we finally got smart and made it really simple and just have just park the slit. And you know, there may be times when you know, there will be some signal from the Earth's air glow in that, but we actually will only read down part of the data. That's what we do. So we can, you know, exclude the piece that we don't want within some limits.
Well, I mean, spectral resolution is a function of slit width too.
Yeah, but for a star, it's a point source. So basically, it becomes essentially like a really narrow slit.
It's not that narrow.
It's narrow enough. They're relatively broadband, you know, broad emission spectrum in a star. We're using hot stars, so we're not looking at the ones that have really a lot of bright features. They're more sort of a continuum, the hot stars.
So you're just using stars for calibration?
Right. And actually for the O2 occultations, it's just a relative measurement of the star. Relative brightness of the star. That's what we're doing with the occultation. We can talk more later. All right, this, you know, I was saying something about the spectrum, how it is. This just shows this. Again, this is just a disk, like it's scanning the complete disk, and you can see as it goes across at night, you only have this atomic oxygen emission at 1356. And as you get into the day side, there comes all these day glow emissions, and as you start falling off the Earth over here, you start, you know, there it starts receding. And again, I just have this is just goes across here, and you'll see these auroral emissions here start appearing as a band up there. So this is that gives you an idea of what the scan will look like. So it's you know, and these observations we have it laid out such that we, you know, if we do a stellar occultation, we won't do a limb scan. We have a 30-minute cadence, so we can add up data, average data very easily, rather than trying to piece together sort of odd time chunks. Day and night, at some point we start devoting one channel to looking at the night side because the emissions are so dim, and we need more time on it to improve the signal of noise. Eventually we switch both over to looking at night because there's not much of the day side to look at. Just to give you an idea of the stuff that we'll be looking at. This is, again, thanks to Stan Solomon, using a timed model and using his globe model. Actually, I'm sorry, it wasn't using globe here, it's just using timed general circulation model. And it's again, these first frame here, I will shows the electron density. So we really will see the auroral region, and as this is during a storm, so you see the stuff brighten at some point here. Okay, then it goes to the neutral temperature. So there is the storm. So the neutral temperature goes wild during the storm, that goes quiets down after the storm. And we can look at the O to N2, the composition ratio. Again, it goes, you know, lots of activity, lots of changes during the storm. And finally, look at the electron densities in the F region. At night, we'll be able to see these emissions from this region. That's what we're looking at night. The daytime, it's there, but it's just a contribution to the signals we get. So in reality, all these things are happening at once. I was showing you just one at a time there earlier, but these are all happening at once. So this is sort of the storm's going on, so the temperature is changing, the composition is changing, and the electron density is going wild. So we're imaging the disk from approximately this vantage or approximately this location that these are shown from. And the imaging cadence we have is about 30 minutes for this.
Do you care where you were looking at the globe?
Okay, good question. Because this is working with a commercial provider, this is one of the questions that came up. And I guess, being a hitchhiker, you can't be too much of a chooser was our attitude. So we said, okay, anywhere will work, but we really would like to be over the Americas. So at some point they said, gee, there's this really nice mission coming up. That would really work well for you guys. So the timing worked nicely. They had an opportunity that really fit and really suited it's almost ideal location. So we, in a sense, we got lucky, but we were saying we can do this from anywhere because we were afraid that it could be, even with 3 satellites a year, it could be a long wait getting if you get too picky about where you're riding, and you're just a hosted payload. That's what they call these.
But why do you care? I mean, you can correlate with other things that people are concentrating on in North America? Or?
Well, the only reason we care is there is a lot of ground-based observations in North and South America. And, a lot of the people who are paying for this are in North America. So, NASA is paying, of course, coming through NASA, the money is from the taxpayer. So it's sort of nice that NASA can sort of show people pictures of, what's happening over Boulder on a given night, right? So that was our really reason for our preference. You get over the oceans, and there's not really a lot of ground-based. There's not a lot of ground-based data. There's not locations for it. But over North and South America, there's a lot of instrumentation on the ground, which normally, a satellite, you're looking for coincidences, and it's really tough getting coincidences. Surprisingly so. You'd think there'd be lots of them, but the satellite's always, coming over a little bit before your observations you had good observations on the ground before whatever had happened, or after, or it's off one side or the other or something. So, this is really great for ground-based coordination with the ground-based observations. Yes.
You've shown how the scientists have been able to model the disk image from other data. Can you describe how having real images of the entire disk can help the scientists?
Well, yeah. Actually, I have a little bit of comment on that later. Ask me again when I get to the slide that has about some of the benefits of this. Okay? I'll try to hit that again. If I don't hit it enough, remind me. And well, actually, sort of getting into it a little bit here is that with sort of a typical model, just sort of the generic empirical models that are averaged over space, significantly averaged over space and time, you get very smooth results. But if you start folding in some of the details of what's happening in the lower atmosphere, sort of some of the more spatial variations, it does have effects on your results of your ionosphere. And people have known for years that there's a lot of variability going on there, and they just didn't have data to track some of this. And that was one reason we came up where we got into this is people had done UV imagers before that looked at composition. Timed mission, Goovy on timed mission did composition. There have been a few others that looked at composition, but the temperature at least images of the temperature on the disk is something that people hadn't done. And one of the guys on the team was saying, okay, well, we'll need densities. And we've sort of struggled back and forth with that, and someone pointed out that if we had the temperatures, we're sort of equivalent type of information. So it gives us a sort of two important quantities to help us understand what's happening in the atmosphere. And that, of course, it helps us constrain the models in ways they haven't been able to constrain them before. Because we had composition, but with composition is not enough. You could be changing the temperature, and that it changes with temperature also. So if you know the temperature and the composition, it's for gas, that's important pieces of information to help specify the state of the gas and or our upper atmosphere. So, and just to I throw this up only momentarily to show you how confusing some people's view of this is. There's lots of stuff going on here, most of which we don't look at. And I guess the winds is one of the reason I pull this in is there's a lot of things about here about the neutral winds, which we aren't measuring, which do make a difference. But fortunately, there's another mission that was selected at the same time, the ICON mission, which will be flying in Leo, and we'll be looking at some of the winds and at the Earth, some of the missions from a different altitude, a different viewing angle, which is really complementary to what we're doing. So I think this is a simulation some people at Goddard did, and it shows you in a moment here sort of how the scanning goes. I won't probably don't want to go through the whole thing here, but it's just a simulation of ours. Shows scanning the northern latitudes and the southern latitudes. The ionosphere is they've done fabulous things with the ionosphere to make it look much more exciting than it typically looks, that I've ever seen it look, but it does stand out. And it shows the icon viewing the limb. So these will be flying, observing coincidentally, assuming we keep somewhat on schedule, somewhat close to schedule. So
is that like 10 or 20 minutes to scan?
Well, for our scan rate, we have set up plan to do a disk scan every 30 minutes and a limb scan or an occultation. So the reason, of course, we want to keep it on a 30-minute cadence so we can form 1 hour, 2 hour type averages and have something that we can sort of routinely work with for averaging multiple days, months of data, whatever.
I like to point out, I worked on the time mission. It takes a month to get a global image because if you're in Leo and you're just looking at little points. Right. You're getting a whole image in 30 minutes. Right. So that, and that's for the, those simulations that I was showing of the temperature and the composition changing the upper atmosphere. One thing I didn't emphasize in that is but you can see it, how quickly it's just on the order of an hour, the whole upper atmosphere is changing. And it's different in different places. And so this global context is something that's very difficult to get from a LEO satellite. Now, here's just a little bit about Thermosphere. Basically, there's a lot of solar observations. This provides us some information about what's happening at Earth to provide sort of a correspondence between what the sun's doing, the sun's output is, and what's happening in the Thermosphere Ionosphere system, which is a set of data that's very valuable for making use of the solar data. Of course, the models, since we got some observations that haven't been available before, at least the images of the temperature across the disk of the Earth haven't been available before. Having that will change what we understand about the models, or at least give us a significant test of models I've never had. Of course, this I mentioned about how it affects GPS and communications and stuff like that. And this is actually one of the guys on the team, his kids. He was showing them the image, so they were really fascinated by it. So, at least to some people, it has appeal. So we'll hope to see an even wider audience. Just in summary, sort of got I think I've hit on some of these things about the forcing from above and below. basically because I didn't emphasize that a lot, the same images is just different processing to get the composition and temperature out of it. So we're doing these at the same time from the same locations. And because of being able to look at the same locations over and over versus flying around and taking a month or at least a day to get back to the same longitudes, we can separate, in the Thermosphere Ionosphere, the changes are in the order of an hour. But from a LEO satellite, it takes, at least if you're covering more than just really low latitudes, just going around the equator, it takes you about a day to get back to the same longitudes. So essentially your image cadence for the Earth is about a day. But from geostationary satellite, we can do this at half-hour cadence, ideally. If we had enough, it depends on what the signals are, and we can separate differences between the time and location. Okay, talked about how we get basically it's like a big pipe to the ground, just drinking from a fire hydrant with all the data, and this by having a global scale picture, it provides context for those locations on the Earth, for radar sites, ground-based observatories, and for LEO satellites. And I guess next week, the instrument gets bolted on. So what the 12th of August, a bunch of us are going to Toulouse and sip French wine. Nitrogen too, I guess, right? Same stuff we have over here, but it'll be even better with the French wine. At the moment, it's scheduled for late 2017. It's a 2-year mission. It's a 15-year life satellite. These sorts of instruments have lasted for decades in orbit on other satellites. So there's hope that we would be able to have some sort of extended mission and have more than just beyond 2 years. Okay, so I'll stop there. Okay, thanks.
This is a very naive question.
Thanks. Okay, all right.
So, will the data streams continue beyond the 2? Is the 2-year because of funding for Earthside analysis, or what's the?
Well, what happens? The way NASA works is they set it up such that there's a definite time period that they funded you for. Beyond that, you have to have see that the instrument's working, that you're getting useful data, and convince a review panel that yeah, this is still worth continuing. It's just still interesting science to be done. So yes, but it's something that you have to go back and they just just to make good use of the resources that they have people re-propose for extended mission. And after a couple of years, you hopefully have got this down so that you can do this less expensively. So they're going to sit there and twist your arm to see how cheap you can get it, right? Okay. Anything else? Yeah.
How long does it take to get up to geosynchronous orbit?
Oh, yes, okay. Of course, off the ground is really fast, right? And then you go to snail's pace. We were thinking, okay, in a normal chemical transfer takes like a day, or less, right? This thing, it's not clear exactly how long, but it's approximately 5 months. So, it was just a different thinking that you were used to having to have the thing.
Reschedule your vacation.
Yeah. It's like okay. Now we sit and wait, and we're used to having to have in thermosphere stuff that heliophysics. You're used to having the thing get on orbit because it's not that far away. The Thermosphere Ionosphere isn't, but.
Can you do anything on the way up?
No, that's we've discussed that, and there's several reasons for. One of the big reasons for that is they don't always have links with the satellite. Their whole system designed so that the links to the satellite are when it's in geostationary orbit, and when it's in orbit, they actually have multiple ground stations. They have guys. You're used to air traffic controllers, right? You know what those are? They have satellite controllers. They have guys sitting there 24/7, a group of guys who sit there and keep track of these satellites. So you got a guy, he's sitting there, I don't know, you know, he'd be maybe running 4 or 5 satellites. And, you know, and if there's a problem, they can transfer it over. They have multiple ground, you know, there's like 20 ground stations or something. Several of those can control the satellite. Is the way they've got the systems, at least a few years ago is the way they had the system set up. I'm sure they still do, because if there's a problem, they can transfer it to, you know, like the location where there's a lot of the engineers, so they can troubleshoot the problem. Otherwise, you got, you know, less, you know, guys who are basically former air traffic controllers. I think is what most of them are. You know, they've worked for the military and they've gone to work for the satellite, one of these satellite companies, and they sit there and, you know, they're used to sitting there for 8 hours, you know, with the screens, and they got things set up such that even though they got 5 different brands of satellites, there's one display for the same display for all of them. You know, they're watching the temperatures and you know, make sure everything's staying healthy, that they don't, you know, run the batteries down too far, something doesn't go off, mess up, things doesn't start looking, you know, veering off. When my satellite TV goes out, I always figure it's something, you know, for a few minutes it's getting flaky. I figured, okay, they were, you know, the satellite was wobbling a little bit or something. So, okay, yeah.
When you found out the propulsion was going to be electric, did that cause you to have to redesign anything with regard to preventing pollution of your optics, basically?
No, actually, it was sort of a. No, we'd planned that we'd have things closed up for a while anyway, that let it outgas. We'd been figuring we'd have to sit there for a month or 2 on orbit to make sure everything outgas. Because, you know, it's a big bird. There's a lot of material in there, and you want to with UV optics, you're always very sensitive to it. So we wanted to let it outgas. So once you know, now we've got more than even more than we'd hoped for.
Didn't cause any big change then?
No change,
Yeah.
really. Other than, okay, well, we're going to sit on our thumbs a little bit longer than we planned. Yeah, we figured it's going to be a week or something, and yeah.
Really basic question. So the imaging device emits UV light. Is that correct?
It measures UV light.
UV light.
Yeah, right.
Okay. Measures UV light, and it's using UV light to isolate the thermosphere.
Yes.
And
ionosphere.
pass through the stratosphere. Okay.
Yeah, because we can, you know, there are emissions that we can. If you look at the spectrum, you can look at the ratio of different brightness of different emissions. That tells you how much of the stuff is there, because the same sun is shining on both of them, all the atmosphere. So the ratio, the ratio of the emissions reflects the ratio of the densities in the atmosphere. And, you know, I didn't get into it, but the bands, you know, depending on the temperature, they'll get broader. Just as you may know that atomic lines do that, also broaden with temperature. But bands do it a lot more. It makes it a lot easier. You know, where atomic lines, you'd have to have a phenomenal resolution, you know, tenths of an angstrom or better resolution. With molecular bands, you're looking at angstroms. Several angstroms resolution is sufficient to see the width changes in width with temperature. Yeah. Okay.
Thank you.
All right. Thank you.